So good day to you all. For this presentation, our topic will be dynamics of rotational motion, and again we will try to solve them with examples given by our book, the University Physics book of theories. Now let us go to the first problem. Problem 10.15. A wheel rotates without friction about a stationary horizontal axis at the center of the wheel. A constant tangential force equal to 74 newtons is applied to the rim of the wheel. The wheel has a radius of 0.13 meters. Starting from the rest, the wheel has an angular speed of 14.5 revs per second after 3.78 seconds. So what is the moment of inertia of the wheel? So let us first identify our given. So we have a tangential force of 74 newtons. We have a radius of 0.13 meters. We have the angular velocity of 14.5 rev per minute and a time of 3.78 seconds. So what is our moment of inertia? So the equations we need to use in order to find this moment of inertia is F tangential times the radius is equal to the inertia times alpha, or the angular acceleration. And the angular acceleration is equal to the omega over t, or angular velocity over time. So to solve for this, we first need to convert our angular velocity. It needs to be in rad per second, so we need to multiply 2 pi rad over rev times minute over 60 seconds so that we can convert it into rad per second, which will give us a value of 91.1 rad per second. Now we can plot it in. So angular acceleration will be equal to 91.1 rad per second over 3.78 seconds, which will give us a value of 24.1 rad per second squared. Now, we derive it from the original formula to get the I, or the inertia. So to leave the inertia at one side, both sides will be divided by the angular acceleration. So our formula will be F tangential times the radius all over angular acceleration. And now we just need to substitute 74 newtons times 0.13 meter all over 24.1 rad per second squared, which will give us a value of 40 kilogram meter squared. That is now our moment of inertia. We can also solve for this in a different kind of solution, wherein you will get the inertia through mr squared, but it's kind of long, so this is the best and the shortest possible way to answer this. So now we have our next problem. Problem 10.18. We can roughly model a gymnastic tumbler as a uniform solid cylinder of mass 67 kilograms and a diameter of 1.20 meters. If this tumbler rolls forward at 0.60 rev per second, how much total kinetic energy does it have? And what percent of its total kinetic energy is rotational? So we have a given. So it's a solid cylinder and a mass of 67 kilograms, a radius of 0.60 meters because a diameter is equal to, or rather, a radius is equal to 1/2 of diameter. So 1/2 of 1.20. And we have the angular velocity of 0.60 rev per second. Now, what is our total kinetic energy, and what is the percentage of the total kinetic energy of the rotational? So the equations. We have the total kinetic energy is equal to the linear kinetic energy plus the rotational kinetic energy. So for the linear kinetic energy, it's equal to 1/2 mv squared, which is the velocity. Our kr rotation kinetic energy of rotation is equal to 1/2 inertia times angular velocity squared, and our inertia is 1/2 mr squared. Since it's a solid cylinder rather. Now for the solution. So let us first solve our kinetic energy for rotational. So we substituted the I with 1/2 mr squared. But first we need to look for our, or rather we need to convert our angular velocity since it's in rev per second. Again, in this kind of problems, it needs to be in rad per second. So 0.60 rad per second multiplied by 2 pi rad over rev, which will give us a value of 3.77 rad per second. Now we can plot it in. So 1/2 times 1/2 is 1/4. So 1/4 of 67 kilograms times the radius r squared 0.60 meters squared times the angular velocity squared, which is 3.77 rad per second squared. Now our total kinetic energy for rotational will be 86 joules. Now for the second part of our solution, we need to find our linear kinetic energy, and for the linear kinetic energy we need to use 1/2 mv squared. But since we don't have an mv, we need to, or rather we don't have a v, or the velocity, or linear velocity, we need to use this. V is equal to r omega, or radius times the angular velocity. It will be then 0.60 meters times 3.77 rad per second, which will give us a velocity of 2.26 meters per second. Now we can plot it in. The linear kinetic energy is equal to 1/2 times the mass of 67 kilograms times the velocity squared, which is 2.26 meters per second squared, to give us a value of 171 joules. So to get the total kinetic energy, we need to add both the linear and the rotational kinetic energy. So 171 joules plus 86 joules will give us a value of 257 joules. That is now our total kinetic energy. And to get the percent of the total kinetic, or rather the percentage of the rotational kinetic energy, we need to divide the kinetic energy of the rotational over the total kinetic energy times 100. So this is our formula. And then 86 joules, which is our rotational kinetic energy, all over the total kinetic energy of 257 joules times 100 will give us a value of 33%. That is now our final answer. Now for our last problem. An engine delivers 177 horsepower to an aircraft propeller at 2,500 revs per minute. How much torque does the aircraft engine provide, and how much work does the engine do in 1 revolution of the propeller? So again, let us identify our given, so we can solve it easier. We have a power of 177 horsepower. We have an angular velocity of 2,500 revs per minute. A torque, which we need to find. For the equation of this, power is equal to torque times the angular velocity. And for our second problem, we need to use, because we are looking for work, work is equal to torque times the change in angle, change in theta. So to solve for this, we need the torque, so we need to leave it on one side. So torque will be equal to the power over the angular velocity. But first we need to convert. Our power needs to be in watts, and again our angular velocity needs to be in rad per second. So 1 horsepower is equal to 745.7 watts. So we need to multiply the 177 horsepower to 745.7 watts, which will give us a value of 1.32 times 10 to the 5th power watts. As for our angular velocity, we need to multiply it by 2 pi rad over rev times the 1 minute over 60 seconds, which will give us a value of 261.8 rad per second. Now we can plot in our given values. So 1.32 times 10 to the 5th watts all over 261.8 rad per second should give us a torque of 500 joules per rad. That is now our torque rather. Now we need to look for the work an engine do in 1 revolution. So 1 revolution is equal to 2 pi rad, and in solving again this kind of problem, it needs to be in radians. So 500 joule per rad times 2 pi rad. Our work then will be equal to 3.17 times 10 to the third power times 10 to the third power joules. That is now our work. Now that's all. Thank you. If you have any questions or clarifications, you can just comment or you can email me at my at my email. Thank you very much.